Good afternoon, everyone. My name is Suresh Rajgopal, and I'm here with my colleagues Katya and Sujit. We're going to be tag teaming today, talking to you about what can storage do for AI. So I think everyone knows what AI needs from memory. So you need more bandwidth, more capacity. And I was initially going to say it's not very obvious what AI needs from storage, but I think after the talk we just had from Pratik, he painted a really good picture of what storage can do for AI. So he's kind of made some of my job a little easier in terms of what we'll be talking about. So here's a picture of the a visual view of the AI pipeline, and Pratik talked about it in great detail. The content on the left is a lot about the ingestion and the capacity storage and the prep of the data for the training. And we want to be talking less about that today. Our focus is really the content on the right. And so what do we have on the right? We have model training, so large foundational model training, small language model training, fine-tuned models, and then we have inference, so cloud inference or inference on a PC. We also have content on, there's work related to RAG, which I'll be spending less time on. Our focus is really more on learning about what storage can do here and how can storage help here. So to begin with, we want to structure this in a way where first we want to make the case for why flash storage needs to play a larger role in training and inference. So I'll spend some time talking about that and trying to motivate the need for that, and I think Pratik did a really good job of that, so I'll kind of work through a little more material on that. Then my colleague Katya will highlight some of the opportunities where flash storage can contribute. So there's been work done in the research community where storage has been used to contribute towards training or inference. And so she's going to walk through some of that material here. And then lastly, Sujit will go through some examples of what we did where we tested some instances of inference with respect to storage to see what we learned from that. And I thought it'll be useful to share our results there. So let's look at some of the impacts of training. So typically there's cost, there's power, and then there's time. So if you look at cost, did you know that foundational modeling training can cost close to $1 billion by 2027? So, and we're talking about models here greater than the sort of the 1 trillion models that are out there today. So it's certainly a huge factor in cost for training. If you look at time, just comparing the growth of the models going from, say, the Llama 2 to the PaLM model, you're seeing a progressive increase in the time it takes to complete the training. And all of this is happening while your GPU utilization is hovering around 50%. In fact, Pratik showed the Llama 405B model had about 41% utilization. So your most expensive, power-hungry resource is being underutilized here. Talking of power, Google just reported a 48x increase in their greenhouse gases due to AI in the data center. So what this all means is that foundational model training is really going to be accessible to only a select few, those who can afford the cost, afford the power, and afford the time to do this. What about the rest? So there's this need to democratize training. And this picture here illustrates this really well. If you look at the graph, it's a little hard to read, but it shows time versus cost of training in log scale. So in 2009, it cost a penny to train, 1 cent. Over the last 14 years, it's close to $1 million to complete training. And that's about a 3x increase on an annual basis. Now, I'd encourage people to check out this website, epochai.org. They do a really good job of breaking out the cost of training. So they look at the hardware cost, upfront cost for acquisition, but also the energy cost for training. And they've done this across a wide range of models, not just LLMs, recommendation models, computer vision models, CNNs, et cetera. So if we talk a lot about AI trying to unlock the power for businesses, but if we really want to be able to make AI accessible to the wider community, we've got to address this cost curve here. And that's one of the reasons why offload becomes an interesting topic. So how is this problem solved today? So AI training today relies all about keeping that training data close to the GPU. And Pratik talked about this. What kind of data do we have? We've got model parameters, weights, and biases. You have optimizer states that exist between your training batches. Then you've got gradients, which are adjustments you make to the parameters as you complete a pass. Then you've got checkpointing data, which Pratik talked about at length, which needs to be stored. And then working memory, which is forward and backward parsed intermediate storage while the neural network is operating. So for about 1 trillion parameter model, a GPU requires us around 30 terabytes of what I call operational training data. And this is only expected to grow. You've seen the growth charts that were shown in the presentation before this, with your model size growing and your context size growing, which is the memory that the model keeps. This is only expected to grow. And the way this is being addressed today is by trying to get all that GPU memory as close as possible to the compute function. So this is done by aggregating this GPU memory and connecting all those GPU memories through an NVLink. So you can connect it across multiple GPUs and multiple GPUs across multiple servers in a rack. And then the other component that comes along with this is a significant software element that the data scientists spend time doing, which is taking the model, the data, and parallelizing it. So you have multiple batches of model going into different GPUs. So that's data parallelism, you have model parallelism, you pipeline the steps of the training, as well as you have context parallelism. The thing to possibly recognize is every AI server, along with the GPU and the GPU memory, also has has storage and CPU memory and potentially even CXL. So being able to leverage this heterogeneity while taking advantage of power and cost benefits that these lower tiers offer is the area that we'd like to be able to explore. So I'm going to ask Katya to come on stage now.
Hello, I'm Katya Giannios, and so I'll talk a bit about the offloading opportunities. So I will speak about AI, but in reality I'll be mostly talking about large language models, training and inference. In the past 4 years or so, I think there have been more work done in trying to use storage as well, or incorporating storage into the AI workflow. For example, on the training side, if you look, we have been getting works from Samsung and Seoul University, Flash Neuron. It's the work they have presented. And so the Flash Neuron, for example, it's exploring the usage of GPU direct storage. So they're offloading some of the data structures to using that feature. The other type of work was done by Microsoft. That's the Zero Infinity. Their DeepSpeed team has developed quite nice features, offloading data structures to CPU or NVMe storage. So some of that work was carried over on the inference side. So that's the Zero Inference. So we'll talk about more on those two further. But before that, just to mention a couple of more works on the inference side, we have the FlexGen. That's work that was presented or developed by Stanford and Berkeley. So what they did there, they not only offloaded data structures to NVMe, but they also considered offloading parts of the data structure, so you kind of can specify percentage. Another is Hugging Faces. They have also developed offloading techniques. And in addition, they have incorporated the ZeRO inference into their packages. And lastly, another work done by Apple. So this was the LLM in a flash. So they did inference with offloading, and they even explored different features of the offloading. Like they would talk about the size of the blocks for offloading and so on. We kind of consider the ZeRO Infinity and the ZeRO Inference being in the most mature stage. So that's why we kind of, I'm going to speak a bit about that. And after that, Sujit is going to show our experience with using So the Microsoft DeepSpeed ZeRO Infinity for training. So the ZeRO Infinity, ZeRO stands for Zero Redundance Optimization. So they use a few techniques. The first thing is the way they partition the model. So they partition the model parameters, the gradients, and the optimization. And so they distribute them between the CPUs and the GPUs or NVMe. So here on the right side, I just have put like what the CPU offload would mean. So if you have the GPUs, you offload it to the CPU DRAM memory. And when we say NVMe offload, you're offloading further down the stack to the NVMe storage. And I have taken a small video from DeepSpeed, which, is it showing? No. Okay. So in this video, we can kind of see how the whole parallelization happens and the way they offload to NVMe and then upload back to the different data structures. What they use is that the GPUs are connected with the InfiniBand, and there we have a significantly higher bandwidth. And also, as you can see, like really not only the parameters, but also the gradients and activations are offloaded. So the other key features that they're using are they're using parallel memory access, which means that every GPU gets only the data that they need right on the spot. And after that, you use the very fast InfiniBand connection to redistribute the data structures. The third feature that they use is that they overlap, they do a prefetching, so they're overlapping the offloading with the compute. So in this way, you can kind of hide a bit the slower bandwidth of the NVMe. So in this way, they were actually able to train a trillion parameter model on a one GPU only, using the NVMe storage and the CPU. Now I'm going to move towards the inference. So in the inference, the picture looks slightly different. While the training, it's very compute bound. It's very heavily compute. You're multiplying all the time matrices. During the inference process, we have two distinguished phases. The first one, it's called the prefill phase. This is the phase when you're kind of taking the request, you're reading the request, and processing and calculating the dependence between every word or token in respect to the other tokens in the request. So this is a very compute-bound phase. It's very similar to the forward pass of the training. The second phase is the decoding phase. For the decoding phase, you're generating token by token. In this phase, the compute is not that heavy. You're multiplying mostly matrix by a vector. In order to save some of the calculations, you're actually using KV cache. So the KV cache, it's really two matrices, K and V matrix, and they're unfortunately using the same word KV cache that a lot of people here are associating with something else. But that KV cache gets computed initially during the prefill phase and then carried over to the next phases. And with every token that is generated, a small portion of this KV cache gets calculated and put back into the big data structure KV cache. So that's why if you look there, there are two arrows, read and write. So the decoding phase is actually memory bound and bandwidth bound. So the two structures that we can offload here are the parameters, the multiple parameters, the same as we had for training, and the other is the KV cache. Offloading to NVMe of the KV cache, it's possible, but you pay a price for the fact that you're having a much lower bandwidth. And so there are some ways you can kind of reduce this price, like if you're processing more batches at the same time, that would make the GPU work harder. You can use that time to do your offloading. And we'll see the effect of this. I think Sujit is going to show us some results on that. So now here the comparison between the training and the inference. So during inference, as we said, we can offload the parameters and we can offload the KV cache. Maybe only KV cache to the CPU. This is what the DeepSpeed is doing. They're only offloading to the CPU memory. Although some of these other works like FlexGen, they do offload to NVMe. And I think that with the futures of the GPU direct storage, I think the offloading on NVMe for the KV cache should be possible and should give good results. During training, we can offload parameters, gradients, and optimization states. And now let's talk about the applications for inference. So we kind of can look into having two types of inference applications. The one are called online inference. So those are what you're usually thinking of a chatbot, right? Those are really time-dependent applications. You want your chatbot to be giving you responses within 7 to 8 seconds to see the words coming out. What you care about here is time to first token and total latency. The second type of applications are called offline inference or sometimes batch inference. And so for batch inference, what is important is the throughput, really not that much of the timing. And examples are like the Zoom AI companion, for example, summary doesn't need to come right away, right? It's like I think we can all wait for an hour to get the summary of the Zoom call. The Amazon online review summary, it also doesn't have to be right away. Or any type of daily updates of recommendations for products, news, or movies that gets updated daily. None of those, it's time dependent. So where we see NVMe really contributing, it's here, those applications. And here I'm giving it to Sujit.
So to actually test this out, we try to build a system that is simulating or emulating a workstation class system where you can run some of your inference works. For this, we used a fairly large system itself, but we limited the amount of memory we have. We used an inference GPU and an NVMe SSD to do the offload. We tested a few different models here between OPT 13, 30 billion, and 66 billion to basically see what happens as we scale the model sizes itself. And then we looked at different batch sizes and also various prompt sizes here. For the offload, we specifically wanted to look at what happens when you go from generation 4 to Gen 5 for the NVMe SSDs to see what kind of impact that will have on your inference performance. When we look at model size scaling, this is going from a really small 13 billion parameter model to a 66 billion parameter model. When we use the different offloading mechanisms that ZeRO inference provides today, we can see that CPU DRAM offload obviously gives you the most bang for the buck. You get fairly high throughput, but it's fairly expensive as well. Now, to recoup some of that, the offload that you can get from CPU, you can add NVMe disks, and then you can move some of the offload there. And so, as you see, as you go from, as you increase the model size that you're looking at, your throughput reduces, but your NVMe offload is able to keep up. So even with just 256 gigabytes of memory, you're able to support a 66 billion parameter model for doing your inference. Now, Basically, what that tells you is as you're offloading to NVMe, you can run larger models at the same batch size. We looked at, until now we've seen what happens when you're scaling the model itself. Now, what happens when you're scaling the batch size for a fixed model? If you notice here, the CPU DRAM offload, it helps you get better performance, but as you're increasing the batch size, you start plateauing in how its throughput is. When you go from 80 to 128 to 140 and so on. However, now when you move to NVMe offload, you're able to keep feeding that pipeline, and you're able to keep providing those tokens as you're increasing the batch size. Now, NVMe offload allows you to increase performance, while CPU DRAM offload tends to plateau and falter as you increase the batch sizes. Next, we looked at what is the power efficiency benefits of using NVMe offload. On this chart, we plotted the system power that it would take to generate each token for a fixed model size as we're increasing the batch size. When we looked at the power it takes for generating the tokens, when we look at CPU DRAM offload, as we increase the batch size, your efficiency starts reducing. Whereas with NVMe, once you go past a certain point, you actually start gaining back most of your efficiencies. So basically, another way to say this is your power per generated token improves with batch size for NVMe offload, whereas with CPU DRAM offload, you're constantly seeing that reduction. Now the question is, where is this efficiency coming from? Where is this efficiency improvement coming from? And for that, we looked at, we saw what happens when to the latencies as we are going to the NVMe offload. With the smaller models, most of the model can be hosted in memory, so you don't see a lot of improvement in latencies from going to NVMe offload. But when you go to the larger models, most of the improvement comes from the decode latencies. Now, as we see here, Gen 4 to Gen 5, your prefill latency is about the same, because this is where you're filling your inference prefills with calculating the weights and all that, and getting ready for generating the tokens. Now, the decode latency is where you're getting all these efficiencies from. So as you increase your model size and batch sizes, your decode latency starts having a improvement, providing that improvement in efficiency for you. On the next slide, we're looking at, as we go from Gen 4 to Gen 5, how are you improving your efficiency? For the smaller models, since it mostly fits in memory, offload doesn't give you a lot more. But as you increase your model sizes, you can clearly see that for each generational improvement in NVMe, you're getting a better throughput, and you're reducing latency, and also reducing your power consumed by the system, as well as the SSDs as we go from Gen 4 to Gen 5. Now, in this specific case, our Gen 5 SSD is 20 to 30% more efficient, and it improves throughput inference token throughput by about 25% compared to the previous generation. The biggest takeaway here is the cost benefits of offloading. Now, if you were to run an inference with a 30 billion parameter model, with assuming a batch size of 200, right? If you were to do no offload at all, you'd need nearly 6 L40S GPUs and about 256 gigabytes of DRAM just to be able to run inference on that for a batch size of 200. If you start adding CPU offload, now you're reducing that requirement of all the GPUs. You can make do with just one L40S, but now you need a lot more DRAM to be able to fill that inference pipeline. Now, you take it one step further, right? You can do NVMe offload. With NVMe offload, you're even taking away that requirement of large DRAM. You can reduce the DRAM, but now you add NVMe SSDs to help with offloading that inference. So as you can see here, if you take some fixed numbers for CPU costs, DRAM cost, and NVMe cost, you can see that as you're going from no offload to CPU DRAM offload to NVMe storage offload, the offloading itself can give you anywhere from 4.6x to 4.8x improvement in cost efficiency. And that's huge, especially because you're not spending so much on GPUs. Instead, you can translate that to more DRAM, which is more easily accessible, put those in, make it even easier, add an NVMe SSD, and you get even better return on that investment. Finally, conclusions. Power and cost considerations for AI at scale are real, right? Pratik alluded to this as well. You cannot just keep increasing your footprint for training, inference. At some point, it becomes prohibitive. NVMe offload can offer a real power efficient and cost effective alternative to that. You can not only increase your batch size that you can accommodate, but also you get, which gives you better responses, but you can also support larger batch sizes. For this, ZeRO inference and other offload engines work really well, and we should leverage those. NVMe offload requires, we need to be able to hide a lot of the storage latency behind compute. So you need to be able to build those model parallelizations so that you can hide behind the latency impacts. Large block sizes and use of multiple threads, this obviously helps SSD performance, so that helps directly with offload again. Now for us in storage, we want to move to faster generations for PCIe interfaces, because this gives us more bandwidth, better throughput. Now, and also it increases efficiencies and latencies, so it improves latencies. So that's really where we want to go if we want to help democratize and improve accessibility to inference and training and all that. I think that's all we wanted to cover today. Any questions that you can answer? Yeah.
Do we have a mic?
Yeah, go ahead.
So the first question is, what bandwidth did you assume for your NVMe drive? And if bandwidth is the bottleneck, could you get even better performance by using multiple NVMe devices? And the second question would be on latency. So your requests per dollar look great, but what about latency, like inference latency?
So the question is, what are the bandwidths that we are looking at for NVMe generations, and does that have an impact on the performance? So some of our empirical observations seem to point that our throughput is reasonable. Both Gen 4 and Gen 5 are able to sustain them, and adding multiple drives does benefit. But since the data sets, unless you go to much larger batch sizes, is fairly small, so most single drive solutions can satisfy that. And again, for this particular testing that we did, we tried to focus on a system that emulates a workstation class system that you'd have on your desk or something like that. So a single drive is more typical for those use cases, and the throughput that a single drive can provide is sufficient for that. The second question around the latency, obviously the latency from NVMe devices is lower, but we can mask a lot of that by increasing the batch sizes and also doing parallel inference queries so that you're able to process more queries at the same time. And so you have the pipeline filled and get better performance through that.
Yeah, I guess one other addition to what Sujit was saying, we did test different PCIe generations. Actually, when we went from Gen 3 to Gen 4, we saw a significant benefit. We didn't see commensurate benefit from Gen 4 to Gen 5, which kind of, we did see an improvement, but it wasn't the same magnitude. So which sort of points out that it's possible there may be some overhead higher up in the storage stack that potentially could be limiting that. So that's something for us to look into further.
So could you comment on the experiments, like how much of the GPU utilization that impacted once you're uploading stuff to NVMe and things like that?
So the question was how much of the GPU is utilized when you offload to NVMe. So the GPU is still heavily utilized for holding the model itself and also doing the actual inference. What we are offloading is the model weights and some additional KV cache away from the GPU. So when you're still doing the inference, the GPU is still heavily utilized.
I guess I meant the compute utilization. That's like in the beginning, I think on the previous talk, but the optimized system is 41%. So if we start uploading some of the data to NVMe and have to wait for it to come up, does the compute utilization get impacted?
There is a small improvement just because you're increasing the batch size. With increasing the batch size, you're giving more compute to be done, to be performed. So the GPU, it's slightly better used, but we haven't quantified.
Understood. So
Yeah.
you enable higher batch size because of the NVMe support? So
You're giving door to the storage, so you can increase your batch sizes.
Any other questions? Thank you.
Thank you, everyone.